Welcome to Apricot 2021. My name is Anna, and I will be your MC for this session. We are now at our last technical session for today, which is covering IPv6 deployment. I'm sure we are all learning from this session, so we want to hear your questions or your comments in the presentations. If you want to ask a question or write a comment, you can either use the raise hand function in Zoom, and you will join the queue for voice question, or use the Q&A button in Zoom for text, and I will read your question or comment to the speaker. I'd like to remind you to be mindful of the code of conduct, which is published at the conference website and in the chat box. I am now inviting Kenny Huang from APNIC, who will be moderating this session, to give his welcome remarks and also to introduce our first speaker. So over to you, Kenny.
Okay, right, thank you. Good afternoon, everyone. Welcome to the IPv6 deployment section. And we have three distinguished speakers. I'd like to invite the first speaker, Jeff Houston. He's going to give us an IPv6 deployment status update. Jeff, can I return to you?
Of course, Kenny, and thank you. Let me seize the screen and start some pretty pictures running. So let me share this and go full screen mode. Oh, what fun. So this is looking back at the last 12 months for IPv6, a status report for 2020. And so I'll start with a whole bunch of pretty pictures so you can relax. They'll move past at almost a movie pace. And then we'll get into some commentary about what happened in terms of a deeper understanding of 2020, the year of COVID, and whether it had any impact on the momentum of IPv6 deployment. Kind of questions that, you know, at the end of this hour, you'll have answers for, right? Where is this deployment activity happening at the moment? Where is it widely deployed today? Where are the active areas of growth? And has COVID-19 across the last 12 months really managed to smash these V6 deployment activities, or did they proceed anyway? What's going on? So firstly, the overall picture, and here is, you know, the last, I think it's 7 years of IPv6 deployment as measured at the user level. And so we use this technique of sampling users around at random between 7 and 12 million users every single day get sampled for their IPv6 capability across the entire internet. We actually give them a V6 only URL, that's the blue line. We give them a dual stack URL, and we expect them, when they can, to use V6 even when it's dual stack. Sometimes they don't. The red line is the folk who prefer to use 6 when there's a choice. The gap between the blue and the green is, of course, the folk who use V4 anyway. So 2019, relatively big year, up from sort of 19% at the start of the year to around 24, 25% by the end of the year. 2020, a little bit more subdued. And oddly enough, and there's probably a bit of quirk of statistics going on, slight drop at the start of 2021 of a couple of percentage points, but relatively slower. So the big picture was, yes, we did lose some momentum. Here are 3 maps in sequence. Start of 2019, black is, you know, nothing's going on in V6. Green is, well, nothing to do because we've done a lot. And yellow is kind of in the middle, about 50% of users in that particular economy. So 2019, 2020, India. America's gone a little bit greener. Greece went a little bit yellower. France. 2021, bit more in France. Something happened in Peru. Or is that Ecuador? It's Ecuador. Testing my geography. And there was a certain amount going on, but, you know, bits and pieces. So the sequence certainly going slightly green. Let's focus on Asia. Well, India had a massive momentum, but there are other countries as well, particularly in Southeast Asia, and we can certainly isolate Vietnam and Thailand and Malaysia as being of interest. Vietnam, big year in 2018 and 2019, and certainly 2020, once they've got around 40%, sort of plateaued off, small amounts of movement in Vietnam. Myanmar, massive, from 0 to hero, nothing to around 20% across the last 2 years. So quite a concerted effort in Myanmar. Thailand, it's been somewhat longer. They're now up at 40%, and this is over a 4-year period. So that's sort of gradual but continued deliberate momentum, just turning it on one by one. Malaysia has a very similar kind of profile where it has just been a steady but continuous burst, and they're actually right up at over 50% now at the end of 2020. 2019 and 2018 actually were big years for Malaysia. 2020, more about consolidation. The Philippines, where we are now, whatever happened was amazing this year. It is only at around 12%, but most of the work happened around May of 2020. Quite a concerted effort in the Philippines in just 1 month. So some large mobile provider, I would guess, without remembering the details. Moving further afield into Western Asia and the Middle East, Saudi kind of was a bit of a silent mover. Because of that spike, the graph scale has been altered, but they are at 30%, and actually 2020 jumped from 12 to 30%. They basically doubled, and that doubling was in the last half of 2020. Quite an amazing effort in Saudi Arabia over a very short amount of time. So big push. The United Arab Emirates equally up around 30%. A lot of that work in the last 2 years, 2019 to 2020, and the second half of 2020, the numbers came down a little bit. Not sure why. Israel was another quiet achiever, up from almost nothing at the start of 2019 to approaching 20% by the end of the year. Also looking at South Asia, where India just is totally killing it. 2017 with Bharti Airtel in particular, just simply doing it, and then everyone else following suit in very, very short order. The numbers in India are huge and continue to be massive, 70% by the end of the year, predominantly in their mobile networks. So an astonishing achievement. Sri Lanka, smaller country, of course, and APNIC was there. Oh, God, you tested me 4 years ago. Up at 40% now with a massive effort at the end of the year. Nepal, too, has to be mentioned. I'm like, oh, my God, nothing to 12% in just across 2020. And in East Asia, Taiwan has moved from zero to hero. They're up at 50%. And the majority of that was achieved across 2018 and 2019. 2020 was largely static. Japan was a really early adopter, but since that early push that got to around 10%, it's been very slow and steady. So it's been sort of somewhere between 5 and 10% of users per year. And it's continuing on with continuous momentum. The other massive market is China. And there the effort really took momentum in 2019 when they rose from below 5%. You can see a few trials in 2018, and then 2019 was the bulk of it. 2020, more consolidation than sort of massive expansion, and currently they're sitting at around 20%. The whole dual stack thing is a little bit more prevalent there, where there's quite a gap between preferred and capable. South Korea, which did early moves, we're still low in counting in South Korea. We have had long discussions way back in 2015 about whether SKA Telecom, which is one of the big achievers, is actually carrying Google Ads, and our measurement might actually be under measuring in South Korea because of the prevalent use of ad blocking in some of those networks, as far as I understand. Australia and New Zealand, Oceania, yeah, sort of noisy, all over the place, but 2019 took a concerted effort, particularly with Telstra taking initial experiments and turning it on, one of the major providers there. 2020, not so, basically consolidation. And similarly in New Zealand, where basically the work happened in 2017, 2018, the last 2 years have been more about consolidation. Again, a big gap between preferred and capable. We talked to one mobile provider there and got a better understanding of what was going on. And largely that has been rectified. And now folk who are offered the choice tend to go straight to V6 if they can. So I think what we can say is, yes, it has slowed down. COVID did have an impact. 2019, the global growth, 6% of users. Global growth in 2020, 3%. But for many Asian economies, it didn't slow down, as we've seen in those graphs, like Nepal. So who's actually done it? Let's take the percentage at the start of 2019 and the percentage at the start of 2021 and make the difference. Mayotte, okay, so there are only a few people who live there, but it jumped by 62%, and similarly French Guiana. But you can see Sri Lanka, 30% over 2 years, UAE that we've talked about. You can read that list as well as I can. But as you see, there are a number of countries in our region, including, of course, I had it there, Malaysia, Taiwan, India, Myanmar, Vietnam, and so on, that have also done, and Thailand and Australia, astonishing work over the last 24 months. If we break it down year by year, you can see that India has consistently grown each year from 53% 24 months ago to 63 to 72. Oh my God. The United States of America, less so. Very small growth since then. The folk who was going to move have moved, and now it's sort of just over 50% in terms of our measurements. Malaysia, certainly going upwards, not downwards, and Taiwan, slow and steady, 31 up to 43, up to 50. So you can sort of see that some folks certainly dropped a little bit in terms of their relative deployment levels over those periods, while others have sort of maintained it. But percentages lie a lot. Mayotte doesn't have a lot of people. So let's take the estimated number of users and multiply it by those percentages. And here is the number of V6 users that were added over 24 months. Added, new. 161 million new V6 users in India. Even China, the numbers in terms of percentage aren't that big, but they translate to 118 million users. Staggering, an amazing effort. Others from our area, Japan, 15 million new users, Vietnam, 10 million. You can read this table as well as I can. And here, if I break it down a little bit and just look at the annual growth in 2019 and 2020, India had a much bigger year in 2019, 116 million. COVID, I think, did take them a bit of a hit, and 45 million new growth in 2020 says that the effort was actually not able to be sustained as clearly across all the trials and tribulations we've had with COVID, working from home, et cetera, et cetera. So the world added 332 million in 2019 and only 137 million last year. And we can attribute that, I think, almost totally to that dreaded virus, which is what I'm saying here. But actually, this is year by year. We can do month by month, and the numbers are actually interesting. That over the northern summer, there was actually a bit of a pause and a bit of a regrouping. China, the major growth was actually around August, September, October, in that quarter immediately following the northern summer. India, its major growth was in the first part of the year, March, April, May, and things slowed down a fair deal across the summer period, rose a bit in November, but was still down a bit thereafter. So month by month, things were different in each particular country, as I think the momentum of movement. Brazil is another one that's up there, where it moved predominantly in November, that blue line, November and December, rather than any other time in the year. So back to that bigger picture in closing off. What we're not trying to do is build a dual stack internet. That's not what we're trying to be. It's not where we're trying to go. We're trying to go here. We're trying to get to the point where V6 use will naturally die, because when we're all running V6 and we prefer to use V6, there is no V4. So that's where we're trying to get to. The question is, where are we? Now, it's pretty clear that if we kind of push the real data curve into that model, we're about 30% of our way to saturation levels. We're about here. Okay, so let's go somewhere else for a second, because all new technologies follow a relatively similar curve. Whenever I bring out a new technology, whether it's washing machines, cute little mobile phones, any other thing like that, there are enthusiasts who take it up, and enthusiasts may or may not continue. There are early adopters and risk takers that take that idea and develop it. But then there's an inflection point, because when you're trying to move from enthusiast to mainstream, you might not bridge the gap. You just might not get there. And failure, particularly at these inflection points, and this is a big one, is always an option. Once you get to about 80% market saturation, everyone else will happen inevitably. The laggards and the skeptics will just get dragged along. But this failure point, where is it? Because one option says, 2 years ago, the rest is inevitable. We are now mainstream. V6 is now happening. But don't, these are just models, and it could still be in the future. It could still be an option. But if it's an option in the future, what does that mean? Because if it is yet to be an inflection, this is not a discussion about V4 and V6 anymore. No. I actually think V4 is on the, it's not going to be relevant as a global unique addressing plan. So if it's not a tension between V4 and V6 as global addressing plans, what's the tension? And I actually believe the tension is addressing-based networks versus name-based networks. Because in some ways, both of these technologies, V4 and V6, are sort of latter 20th century technologies. They use this destination-based packet forwarding mechanisms and architectures. But we've been playing a whole lot over the last few years, particularly fueled by V4 address exhaustion, into trying to make the address do much less rather than more, and make DNS names and name-based architectures do a whole lot more, and actually be the center point of the cohesion of an internet. And so in some ways, it's still an option that we might not get to the end of an address-based networking plan. The tension of inflection might well be alternative architectures. And it's not new IP. It's not IP as we knew it. It's changing the role of names and addresses and look at networking architectures in very, very different ways over the coming years. And I certainly, the reason why I'm interested in the DNS a lot lately, and maybe you should be too, is that I suspect the DNS and name-based networking computation is offering us much more than we ever thought possible. And as we play in that space, we tend to get better and more flexible methodologies. We get content-based network systems with massive replicated content in ways that we never dreamt possible in the old mode of address-based networking. So that's a brief overview of the world of V6, slowed down in 2020 with COVID, and some discussions about where does it all go from here, and the larger question about, is V6 the endpoint, or is it still a way station on various other ways of doing this? Thank you.
Thank you, Jeff, for your very good presentation. We are now open for questions. As I mentioned earlier, you can either raise your hand for voice question, or you can type your question in the Q&A box, and I can question for you. Okay, it looks like we don't have any questions. Oh, okay, so we have one question from Yanya Khan. Do you consider naming the host versus naming the interface important aspect in controlling the explosive routing table growth?
You see, that's the real question. Because when we talk about name-based networkings, we're way over naming hosts. Host names don't matter in the slightest. We're naming the service. We're naming whether it's Netflix, Yahoo, Facebook, or anything else. It's the service. Hosts have disappeared inside this architecture. We're now talking about massive replicated service and content, and trying to understand networking architectures that support replicating the same service almost down to units of population of a few tens of thousands. So we're replicating this 1 million times around the world. Those kinds of architectures of networking, you're no longer talking about hosts and addressing hosts. They're kind of old school. We're talking about services and client. And it's that architecture that I think is going to drive the future of networking. So it's a mind sort of warp going from where you were, 2 points, network in the middle, host to host, into a service that you want to spear around the entirety of a network and have users access the closest iteration or instance of that service. Think about a shopping chain. I want to go to, I don't know, McDonald's. Both of us can go to a very close McDonald's. It's not the same shop. It's the same food, oddly enough. And that's what networking is trying to replicate, that same kind of replicated service model. Thanks.
Okay, thanks for answering that question, Jeff. Are there any more questions? Okay, looks like we don't have any questions, so I'm going to pass the mic back to Kenny to introduce our next speaker. Back to you,
Okay,
Kenny.
thank you. Okay, thank you. And thank you, Jeff Houston, for giving us very brief IPv6 deployment status reports. And it seems like good news last year, still in Asia Pacific region, IPv6 grows pretty fast. So the next speaker will be Cesar Absin from PLDT, Philippine Long Distance Telecom Company. He's going to introduce PLDT IPv6 journey. Let's welcome Cesar. Thank you.
Good afternoon. Can you hear me now?
Yes.
Yes, we can hear you, Bo.
Thank you. Good afternoon. So, welcome to Manila, virtually, unfortunately. I'm here to share with you, as mentioned, the PLDT's IPv6 journey. So I'm Bong Abisina. You can I'm from AS9299, and let me share my slides. All right. So as a background, PLDT is a service provider based here in the Philippines, offering services from consumer voice and broadband using fiber and DSL to enterprise VPNs such as Layer 3 VPNs, MDF-based Layer 2 VPNs, direct internet access, or IGATE as we call it, to IPLCs. So with these vast offerings, there's so much that drives us to pursue IPv6 adoption in the network and to the services that we offer. So what drove us? Actually, these are still driving us. To highlight some here, our North Star, of course, is to provide the best experience to our customers. And with regards to IPv6, I'm typically asked, what will I get from IPv6? Will it increase my download speed? While IPv6 capability does not translate to a speed increase, we believe that opening up our services to IPv6 internet would allow subscribers to connect to the future of the internet and get the best experience from contents and apps, which would only be available on IPv6. This is also an assurance that we could continue our services to the future and connect even more Filipinos to the rest of the world. Also, way back in 2016, 2017, we started a network-wide transformation program to expand and automate yet simplify the network and anticipate the arrival of 5G and, of course, the proliferation of Internet of Things. It was anticipated that to support these massive connectivity requirements, we must be able to transition and enable the network and the services that runs on top to IPv6. And also, of course, everyone can relate to this one. The depletion of IPv4 addresses is a major driver, so we can continue providing the services to the community. The simple objective is, of course, to enable IPv6 in the network and its services. That's very simple to say, but we have to define first our guiding principles on how to achieve this objective, because as simple as it may seem, and as anticipated and learned along the way, it is complex because of so many factors, which I'll show in the next couple of slides. So our guiding principles. So first one, this is obvious, best customer experience, mentioned earlier. We cannot afford service disruption as we do this, so we must test thoroughly. Second one, this is key because of complexity. So we must identify priority areas. The third one also would help in breaking or solving the complexities involved. So this would be a lot of research and study. Last one is to manage investments, do more with less. I believe this is crystal clear, so we must consolidate activities with business as usual projects. Now that we are guided, we can already look at the details of what to do in the network. Here's a simple diagram. Show my pointer right there. A simple diagram representing the subscribers on the left to the internet service on the right. What's in between is the IP transport network infrastructure. This is us. So where do we start? And how? Do we start on the IGP? Do we start on client routes? What are their interdependencies? Looking closely back at the diagram, it's so easy to get drawn to the complexity underneath. A discussion of an area or strategy to do leads to so many other scenarios and uncertainties, which could lead to another and so on. And worse is to nowhere. So we have to break the network into smaller pieces so we could focus. Going back to this diagram, we identified the IP planes that makes up this network to understand the interdependencies. So breaking up this diagram, as if we skin a specimen to show the different systems would look like this. First one is the infra plane. This is where the IGP is. This enables MPLS and forms the basic building block of the services above it. Second is the service plane. This is where you can find the MPLS applications, L3 VPNs and L2 VPNs, the products and services I mentioned earlier. These VPNs are also both a corporate products or services by itself, or it could be another building block for services further above. And that is the last plane, which is the user plane. This is where the consumer traffic is, whether it's for voice or internet traffic. Now, all these planes are running at the same time in this simple line diagram. The one on top is dependent on the one below. But as interrelated as this shows, they are independent in terms of IP routing, which is a good sign for the purpose of narrowing and focusing on IPv6 activities. And further analysis would show that each plane could have its own IPv6 transition mechanism, again, independent of each other. Having identified the independence of these planes, next is to identify what IPv6 strategy to adopt. At the infra plane, there's nothing else but SRv6. Relatively new, but this is the way to go. We believe that this is the way to go to further simplify the network's programming capabilities by using IPv6 forwarding plane. We've done segment routing, but SRMPLS, and that is because SRv6 unfortunately is not yet available when we started the network transformation. But we plan to further simplify and improve the network, so SRv6 is on the pipeline. The good thing is, even without SRMPLS or SRv6, we can support dual stack IPv4 and IPv6 in the service plane using RFC 4798, RFC 4659, or better called the 6PE, 6PPE. Hope I didn't mix up the RFC numbers there. Anyway, they've been around for quite some time now and pretty much matured, so not much really of a problem there. And by the way, this again proves planes are independent of each other in terms of IP routing. At the user plane, especially the broadband service, there were quite a few IPv6 options to consider, and we identified dual stack as the best choice to simplify the network and minimize service impact. One key thing though, we just have to make sure that when we enable one plane with IPv6, the other planes won't be affected during actual implementation to avoid service disruption. So with transition mechanisms identified, the next critical task is the IPv6 address plan. We developed the address plan around the service offerings, as this comprises the bulk of address requirements. That is from the existing services and client base to anticipated new services and projected new subscribers. For enterprise service, DIA, or direct internet access, we allocated /48 per client account. So this is equivalent to 65,000 networks, 655 to be exact. And with each network having 2 raised to 64 hosts. You can do the math, but of course that's a lot of hosts. But one thing to highlight here is that this address allocation is aligned in terms of, this is aligned in terms of the address block size to the end user block assignment of APNIC's guidance, and not in any way reference to RFC 3177. The challenge though here is client adoption. The DIA service is ready for dual stack IPv4 and IPv6, but needs corresponding client network configuration to make this happen on an end-to-end perspective. And we're hoping that clients would be able to adopt very soon. By the way, IPv4 stays as is, at least for the existing clients. We don't want to mess up with this, at least for now. We're just adding up the IPv6 capability on top of the existing setup. So yes, if you're an existing iGate client, we have allocated /48 for you. You may go and contact your relationship manager to get your /48. Sorry for the pitch, but we're just excited for you, and we're excited to further push and increase the adoption of IPv6 in the country. For broadband internet service, we allocated /56 per subscriber line. So this is now referenced to RFC 6177, and in anticipation of the proliferation of Internet of Things or IoT. /56 is equivalent to 256 networks. Again, with each network having 2 raised to 64 hosts. So that's a lot for one broadband subscriber line. It surely would support this service for a great deal of time, and would greatly support the needs of a small office, home office setup, especially now with the recent and massive shift to work from home arrangement. The /56 is for the LAN, and one link is assigned a separate address space. And with this, the previous, same with the previous service, this is also dual stack for IPv4 remains as is. Parallel to all these activities are the iterative testing of the different scenarios and transition mechanisms. And after testing, next is the actual implementation of the transition mechanism and the IPv6 address plan to the live network. The primary concern, as always, is to minimize, if not eliminate, any service interruption, and we have to open up the network to IPv6 slowly. From the broadband gateway on the right, down to the modem or CPE on the left. And once the CPE is enabled, it would become the final link between the IPv6 ready consumer devices to IPv6 internet. I must say that this is so easy to represent in this diagram, but this is not without its challenges. For one, old ADSL CPEs cannot be upgraded to support IPv6 anymore, and they must be replaced. These CPEs would need a protocol for replacement, and the way to do it is through the separate initiative to upgrade all DSL lines to fiber, and this is already an ongoing initiative. So lessons learned. I already mentioned quite a few, but I'd like to highlight what we learned during the address planning. When we first did the address plan, our reference is the IPv6 address space that we have at that time. And no matter how we arrange it, even upside down, it won't fit our requirements, both for the services and the infrastructure. So many iterations took a while, only to finally realize that we need to justify more and bigger address space to finalize our address plan. So do not scrimp on the addresses when doing the address plan. Think ahead of the services and demand. And one thing is for sure, APNIC is there to help. APNIC helped us on this, and APNIC even helped us in training our staff. So thank you, APNIC team. Thank you, guys. The other is about the implementation, as shown in the previous slide. So slowly opening up the network. This is very important, not just to minimize the service impact, but also to localize implementation and easier trouble isolation when needed. So where are we now? So DIA and IPVPN services are ready for dual stack IPv4 and IPv6. Native v6 is also okay. Unfortunately, actual client adoption is still very low, but we hope that through this campaign and through these sessions, adoption will soon ramp up. For broadband service, we've already brought IPv6 to the end users, also on Google Stack, and that could be seen from the device itself, right there. And these devices could reach IPv6 internet as shown on these screenshots. So that's the ping and reply to IPv6 Studio and Facebook. And the progress, a lot of figures like this was shown earlier by Mr. Jeff. The progress could be validated in this very helpful measurement tool from APNIC Labs. So I took a screenshot, thanks to APNIC Labs. We are there, a little over 30%. Of course, the goal is 100%, and it shows that we still have so much to do. But at this point, we are very happy to contribute and lift the country's IPv6 capability through our network transformation initiative. So that's our IPv6 journey. And to the Filipino community, the future of the internet is already here. And we humbly welcome you to IPv6 internet. Thank you, and stay safe, everyone.
Thank you so much, Bong, for your presentation. We are now open for questions. Do we have any questions for Bong? Okay, so while we are waiting, I do have one question for you, Bong. You mentioned earlier in your presentation about customer experience. So for ISPs who are planning to implement V6, what would be your main advice to avoid service disruption?
Of course, the number one factor there is the testing. So test everything, test all the scenarios that you have, test all the services once the IPv6, whatever solution you have in your plan, whatever that is, you have to test it thoroughly before actual rollout. And during actual rollout, the key there is slowly, as I mentioned earlier, slowly open up the network to IPv6 so that it would be a lot easier for you to isolate and identify if there are problems that will be encountered along the way. Thank you.
Thank you, Bong. Okay, looks like we don't have any further questions, so I am now passing the mic back to Kenny to introduce our last speaker. Oh, sorry. Actually, we have one question from Masagong Nugruho. What is the main reason for PLDT to choose to use dual stack up to customer premises instead of IPv4 only?
I mentioned this already in the early part of the discussion, but again, the major factor that drove PLDT on this one is the network transformation. So we cannot afford to go ahead with just IPv4. We cannot continue the service because with the depletion of IPv4, we cannot accommodate more and more subscribers. So the dual stack was selected because we believe that this is going to have the least impact in terms of customer experience. So we'd like to have the clients to still experience the IPv4 that they used to, and at the same time, in a way, like offering a parallel connectivity going to the IPv6 internet. So we opted not to go through any tunneling or translation mechanism, so that the experience of our customers are kept. Thank you.
Okay, thank you, Bong. Over to you, Kenny.
Okay, thank you, Anna, and also thank you, Bong, to give us the PLDT V6 journey. I think that's a very good reference model, especially for the addressing plan. So let's welcome the last speaker, Parash Khatri from Nokia. He's going to introduce SRv6 technology and deployment use cases. Let's welcome Parash.
Thank you very much, Kenny. And thanks also to Bong, because I think he already sort of gave me a bit of a lead into my session by talking about SRv6. So let me share my screen now. Okay, trust you can see that now. Okay, so very quickly, SRv6, the term itself doesn't really tell you a lot about what it is. It's essentially a technology that is used at what Bong called the infra layer or the underlay. So you could think of it as the core routing layer within a large service provider networks. And the SR actually stands for segment routing version 6, as in it's using IPv6. So if you are going to talk about SRv6, we've really got to talk a little bit about segment routing. So the way I've structured this short presentation is to give you a bit of an introduction to segment routing, and then I'll talk about how we implement segment routing using IPv6, which gives us the SRv6, and a very quick look at some of the use cases it actually enables. So getting into it, the one of the key things that we've got to sort of think about when we are talking about segment routing is what is the actual driver, right? And if you look at how we've built networks over the past couple of decades, they've been actually reasonably simple in the sense that the endpoints of the network were either the users, who were the consumers of the content, and then there was the content, which was coming either from the global internet somewhere or somewhat centralized data centers. But things have changed now. And if you look at this picture, it's kind of indicating all the different endpoints in a modern network. So you've got what you had before, which is the global data centers, or the centralized data centers, the internet, and so on. But then you've got many other things that are taking part in this whole routing process. You've got edge cloud locations. You've got millions, billions of IoT endpoints, and so on. So the key difference between what we used to do before and what we have to cater for now is that the flows in service provider networks are not as well defined as they were. So it's no longer a east-west traffic flow. It's a lot more any-to-any. It's more dynamic. The flows tend to be a lot more elastic. So what we need to do now is to really build networks that can cater to those kinds of flows. In service provider networks, we've typically built this capability using MPLS protocols such as RSVPTE and LDP. What we found is that these protocols cannot actually scale to the level of per flow control that we want in networks of the future. And what we really want to do is to tailor these traffic flows on a per flow basis. So traffic engineering at a large scale, which is very difficult to do. So this is where segment routing comes in. Now, at its heart, segment routing is a source-based routing paradigm. So it's completely different to how we do destination-based routing today. Now, there's a reason that we are seeing a lot of traction in such a source-based routing mechanism. Now, the way it works is that in a segment routed network, the ingress node actually dictates the path any packet will take through the network. Now, this is completely different to how we do destination-based routing, where the routing decision is made by every single transit point between the source and the destination. So with segment routing, the ingress node puts this information into the packet itself. So it encodes this as a set of instructions that will be followed by the rest of the network as it routes this packet to its eventual destination. Now, the key benefit you get out of that is that the network as a whole, the core of the network, the transit routers, do not need to know anything about flows and how they're routed, because the state for every particular flow is actually kept just at the endpoints, the edge routers. So we get rid of a bottleneck that we have with current scaling mechanisms, where there's a lot of state at the midpoints of the network flow. Now that means that we can actually scale our networks a lot larger than we could have done with the mechanisms that we've had before segment routing. So take this example here, where you're routing traffic between router 1 and router 4, and we want it to follow a specific path. So what would happen is that router 1 would put information into the packet that then tells the rest of the network how to route the traffic. So assuming that this was a network where we had a sort of uniform IGP metric across the network, where every link had the same IGP metric, you would expect it to go from R2 to R3. Whereas what we'd like to do is actually force it down to R5 or up to R5 through R6 and then back to R3. So these are things that we cannot actually do easily with the technologies that are available to us. So these segment routing extensions are being done by extending our IGPs. So there have been extensions to OSPF and ISIS to enable us to scale or to carry segment routing information. And I'll give you an example of what that actually means in the next couple of slides. So what exactly is segment routing? And what is a segment? Now, to sort of get a grasp of this, what we've got to think about is, from a routing perspective, there are two topological things that are of interest to us, right? At a very sort of abstract, simplified level, we care about nodes and we care about links. So, you know, you can specify pretty much any path in a network by specifying the set of routers and links that you know, a packet has to traverse as it makes its way from a source to a destination. So what segment routing does is it considers each of these topological elements as segments. So in a simple topological path-based application of segment routing, you'll have nodes that are segments and you'll have links that are segments. Now, what we do with segment routing is that we assign identifiers to these segments so that we can then use them in order to dictate the flow through the network. And these identifiers are called segment identifiers, SIDs, or SIDs, or SIDs for short. And this information about the segment identifiers is actually advertised through your IGP, so that every node in the network builds an understanding of what are these SIDs. So there'll be node SIDs to do with the actual routers, and there'll be adjacency SIDs to do with links between the routers. There are other SIDs, but for our purpose, these are the ones that we're looking at now. Now, given that we've got these SIDs, how does it actually work? And here it's actually instructive to look at an example once again. So we've got a simple network. You've got some provider edge routers, P1 and P2, and you've got a network core built out of a number of provider routers. So think of this as the PEs are the demarcation between, you know, wherever the traffic is coming from, and that could be your customer sites, and the core of the service provider network. So what we've got in this network here is, firstly, we've got a SID that is assigned to each of these nodes. So you can see here, P1 has a SID, a node SID of 200. For now, let's not worry about how that's encoded. It's just a number. It's an opaque number, but it identifies a node. And then you've got identifiers, a similar identifier for links in the network. I've illustrated one here, which is the link between P2 and P5. And that has a SID of 1003. Now, all of these other links will have SIDs as well, but just for the sake of simplicity, we'll focus on this one here. Now, what we'd like to do is we'd like to send traffic this way. And once again, assume that all of the IGP link costs are identical, so that if left to its own devices, traffic from P1 to P2 would either go up through P1, P2, and P3, or down through P4, P5, and P6, assuming ECMP is in operation. But what we'd like to do is force traffic down this link between P2 and P5. How do you do it? Now, if you think about how we could achieve that today, you could use something like RSVPTE within an MPLS context to do it, and it'll do the job. The challenge, as we said, is that for every such tunnel that you instantiate, you've got to have state. So if you built that using RSVPTE, that'd be state on P1, P2, P5, P6. If you built another LSP, that'd be another set of state associated with that. So that's not acceptable. It doesn't scale. So what we do here is use this segment routing paradigm where the routing instructions are put in the packet itself. So in this case here, a packet comes into P1 and we put this information in the packet. How it's done is another story, but let's just assume that we somehow encode this information into the packet. So we've got, at the top, you've got 300, and then you've got 1003 and 800. Now, from a purely instruction perspective, what we're saying here is that we're telling the node, or the network, to send the packet to node with this SID of 300, which is P2. Once you get there, then pick the adjacency to P5, which is 1003. Once you get there, then you take me, we're telling P5 to transport the packet via the shortest path to node P2, which is a SID of 800. So these are encoded within the packet itself. So as the packet makes its way through the network, each node looks at this, it gets to P2, and it understands that it's node 300. It looks at that. It looks at the 1003, and it understands that it's going to send the packet out to P5. So it strips that information from the packet, gets to P5. P5 is left with a SID of 800, and it knows that that means that I've got to send it to P2 via the shortest path. So it sends it via P6, P2. So it's as simple as that. The routers P1, P2, P5, and P6 had no visibility of the end-to-end path. It was gleaned simply from the information that's in the packet. And that's the power of segment routing. So summing it up, this is the change in paradigm where we're routing based on segment lists that are encoded inside every packet. We're not doing destination-based routing. We're doing source-based routing. So now I come to this thing that I asked you to just sort of ignore for a moment, which is how do you actually encode that information in the packet? There are two ways of doing it. One is you use MPLS, and that's an instantiation of segment routing called SR MPLS, and that's where you use a stack of MPLS labels where the labels represent the SIDs. The other approach is to use IPv6. And instead of MPLS labels, what you're doing is you're encoding that information as IPv6 addresses, where a SID is encoded into an IPv6 address. So how do you do it? So this is where SRv6 as a technology comes in. So now, once again, a lot going on in this slide. So let me just simplify it for you. Most of you will be familiar with the IPv6 extension header and the concept of routing headers. A new routing extension header has been defined. It's called the SRH, or the segment routing header. And the express purpose of this header is to carry information about the SIDs to be visited between the source and the destination. Now, you saw that in my example, I had 3 SIDs. So what you do with SRH is to encode those SIDs within this SRH extension header. So if you had 3 SIDs, you'd have 3 by 128 bits taking up space in here, indicating what are the nodes or links that must be traversed on the way to the destination. So that's done for every single packet that is coming in to the network. So very quickly, the way it works, if you've got a customer site or a data center or anything external to the service provider, packets come in from there. What you do is you encapsulate it with an IPv6 packet. Within the IPv6 packet, there's an SRH. Now, there may or may not be an SRH depending on the application, but for more complex segment routing applications, there will be an SRH. Now, let's assume there is an SRH. So you put that in there. This SRH has complete information about how to route the packet. And then you send it out into your network. As it goes to the network, it works its way through the list of segments that are encoded in the SRH until it reaches the destination. So 2 ways to look at it. One thing that's immediately obvious here is that there is a bit of overhead here, because you're talking about encoding potentially a large number of SIDs as IPv6 addresses, each of them 128 bits. So this is where SRMPLS as an option uses 32-bit label. Well, it's actually 32-bit label stack entries. So the IETF has been doing a lot of work on reducing the impact of that on the packet, as in reducing the overhead using some compression techniques. Cannot really go into it right now, but it's I know if you're interested, there's a number of mechanisms to ensure that the overhead is actually limited. Now, given that, what are these use cases that we're talking about? In general, these are some use cases that are tied to quite new applications. So there's a new generation of applications that are being enabled that impose different requirements on networks. So typically we've built networks that had reasonably static flows, and we managed things like capacity management over the course of weeks and months and so on. with this whole dynamic nature of traffic flows, that's that is now a bit of a challenge to do using the traditional means. The second issue is that the SLAs that operators have had to provide to their services are now actually getting a bit more complicated. So while we've always had things like bandwidth and availability and so on, we now having this class of applications that need latency guarantees, as in maximum latency that it can, be subject to as it goes through the network. So we've now got to architect our network so that the latency is minimized on a per flow basis potentially. So this needs new capabilities in the network, which is where segment routing comes in, to be able to route these flows to meet these new requirements. The second area of that is really the high scale. How do we deal with differentiated traffic flows when you've got millions of IoT endpoints? Now, before I wrap up, I wanted to, instead of just talking about a very high level use case, go through a slightly more detailed use case for SRv6. So allow me a minute to go through this. This is a use case for SRv6 in the data center. And we've got an example here where, say this is your typical wide area network. You've got a provider edge device. You've got some sort of core network, and you've got an interface through a data center gateway to a data center environment. Now, when we typically talk about how services are constructed for a data center, we've talked about overlays. So we have this overlay service layer that uses maybe things like EVPN, VXLAN, and so on, that is running across over an underlay. And in general, there is no real interaction between the overlay and the underlay. Now, one interesting thing that SRv6 enables is to actually treat the endpoints in the data center, which are your, there could be your virtual network functions, there could be a containerized network functions. You can treat them as extensions of your underlay. And by doing that, you have some interesting ways of using SRv6. One of the key applications of SRv6 is what we call network programming. And in short, network programming is a way where we can actually encode additional informations into the SID value. We exploit the size of the IPv6 address, and in addition to the location information, it's actually carrying information on some functions that need to be run by the destination once it gets to the destination. We can even pass arguments to this function. So you can see that there is a lot of power in doing that. So this is one very interesting application of SRv6, where you have that tighter coupling between the actual services and the underlay, and then also the dynamic ability to invoke functions at the endpoint once the packet actually reaches it. So let me quickly sum up. The session was predominantly about segment routing, with an emphasis on segment routing over the IPv6 data plane. There's a few very good reasons why segment routing is getting a lot of traction in the industry. It's reducing the impact on the control plane and allowing us to scale our networks much higher. It's allowing us to move from what was predominantly an IPv4 control and data plane in the network core to an IPv6 only network. And one thing I didn't really get a chance to touch on here is that it works really well with centralized programming through SDN control. So thank you very much. That brings me to the end of the presentation, at least.
All right, thank you, Paresh. We already have 3 questions on the line for you. So first one is from Brett. What adoption of SRv6 over SR are you seeing?
Look, so segment routing has been has been around for about 7 or 8 years now, and the initial implementations of segment routing were mainly around SR-MPLS. So SR-MPLS has a bit of a head start. SRv6 is starting to get a bit of traction now. It's I still say we're a little bit early when it comes to in the implementation cycle for SRv6. There is still some work to be done within the standards around this compression. So the IETF has a separate group that's currently looking at how we proceed with that and reduce the overhead to make it a little bit more palatable to operators around there. So in general, I would say segment routing is becoming almost a de facto in terms of how we architect next-gen networks. SR-MPLS has a reasonable degree of maturity. SRv6 is starting to come into its own now.
Okay, so we have our next question from Chairul. Is our SRv6 mandatory for deploying 5G network slicing or CUPS?
No, it's not mandatory. I mean, it's what I would say is that a segment routing capability is, once again, not mandatory. There's many ways you can skin a cat. Yeah, but segment routing as a technology is extremely useful for deploying 5G kind of networks. And out of my experience, I would say that the bulk of the networks that have been deployed to do 5G transport have been built on segment routing MPLS to start off with, and SRv6, I guess, in the future as well. I'd say segment routing is something that really needs to be considered for 5G transport networks. SR-MPLS or SRv6, it's a technology choice that needs to be made by every operator.
Okay, third question is from Yanya. What's your recommendation regarding MTU size for running SR, jumbo frames enabled throughout the SR domain?
Look, I mean, I don't think that's that's totally relevant from a SR perspective. The reasons for choosing jumbo frames or not into any network will be dictated by things other than SRv6. So I'd say there is no direct correlation between SRv6 and MTU size.
Actually, there's one more question from Masagum. We will take this as the last question. There is debate where small medium routers can't run SRv6 due to chipset limitations. Is this true? And how to tackle this problem? Is it using the SRv6 Plus, or are there other methods as well?
Yeah, look, I mean, so firstly, that is true because the fact is that SRv6 requires, for advanced applications, requires the SRH, and the data plane processing for SRH is specialized functionality. So a lot of existing hardware out there cannot natively support SRv6. That'll change over time. It's just like any other technology, that's probably why a lot of the early implementations of segment routing have been around MPLS, which did not require a change to the data plane. So what I would suggest is that it's a more holistic look that you've got to take a look at, especially in terms of brownfield networks. For greenfield networks, I think SRv6, yeah, sure. But for brownfield networks, where you have that limitation on hardware, then you've got to sort of consider what you really want and whether you want to compromise by picking, by taking on a subset of capability when you could use some other technology option.
Okay, so thanks, Paresh. That's the end of our Q&A session. I would like to thank again Kenny for moderating this session, and also to our presenters, Jeff, Bong, and Paresh. I am now inviting you to participate in the poll survey, which should be popping on your screens right now. We would like to hear your feedback regarding this session. And also, this session is recorded, so you can check and view it from the conference website. And of course, we would like to encourage you to participate in social media by posting your selfies on Twitter or Facebook using the hashtag Apricot2021. And lastly, we would like to invite you in the social event after this. We have our cool DJs who will be entertaining us via live stream, so I hope you all join us. That's all for today, and I hope to see you all tomorrow. Bye.
Bye.